So we'll continue with tissue integrity management and talking about the amputations, the types of amputations. So the first thing we'd like to learn about is what is the definition of a prosthesis. It's a device that is designed to replace as much as possible the function or appearance of a missing limb or a body part. And we care mostly about functionality, and appearance is a material problem issue. It's a device that's designed to support, supplement, augment the function of an existing limb or a body part. And that's what I like, actually, is making sure that we understand this. We would like to support, supplement, or augment. Support is for someone to stand or to move. Supplement, someone, let's say they lost the functionality of the right hand, they want to use the left hand to control that. And augment is improved performance with the limitations of a disability. So that's what we would like to. So that's all general, but I don't want to work on, the plastics, traditional, prosthesis. We would like to do something like this, an active myoelectric prosthesis. That's what we're going to call it, myoelectric, because it's using the electrical activity to activate a robotic arm. And this is also called externally powered because it has energy batteries that, power it. But before we go there, we need to talk about the tissue itself. So most common reason for upper extremity amputations, correction of a congenital deformity or tumors. People get amputated because of that. And tumors are commonly seen in young kids from birth to 15 years old. And then trauma. And that's the most prevalent one of them. And this is the most common reason for amputation of inpatient 15 to 45 years old. With tumor being a distant second. So trauma is the most common reason. And then we have upper extremity amputations tend to be rare in patients who are older than 60 because if a person reaches 60 years old, their genetic map is actually healthy, so they don't have tumors. And they'll be more careful and move, so they don't drive fast and do these other things. And if someone is actually reaching 60, the probability for them to reach 90 is, quadruple compared to someone that's young. But then we might have some secondary to tumor or medical diseases, amputations. Now, diabetes is another reason of amputation, especially with the lower extremities, if they're not taking care of their wounds. That's another big problem. And if you remember, we talked about the types of amputations, very important. So if we say transphalangeal amputation, and so I think transphalangeal amputation is the one that is with the fingers right here, because those are phalange, right? And if you have transmetacarpial amputation, that means that you have an amputation, but the thumb is there. And if you have transcarpial amputation, the thumb is gone. So that's completely gone, the amputation. And then you have the wrist disarticulation, which cutting on the wrist itself. And we have the transradial amputation in the middle, and then the elbow disarticulation, transhumeral, the middle between the elbow and the shoulder disarticulation. And then we have something called interscapular thoracic, which means that the amputation is taking part of the ribs and also part of the lungs. We would like to have some residual limb to work with, right? So it's easier for us to work with transradial or transhumeral amputations because you have some muscles that you can work with. Different types of prostheses. We have a very wide spectrum, and then they range from mostly passive or cosmetic, only just plastics, just as an appearance, to the other end. You have a functional prosthesis, so it's either just plastic as something to complete the body, or you have something that is functional. And most prosthesis falls in the middle. Cosmetic prosthesis can look extremely natural, and even we have material that they can have the same tone of the skin, but they're expensive, the material itself, and it's hard to actually maintain. You have to clean it because of all the softness of the material. and expensive, and you just sacrifice some of the functionality to increase the cosmetic appearance of it. What we would like to do is, functional prostheses, we can have them in 4 categories. Cosmetic, the cosmetic appearance is a function, right, itself. Body-powered prostheses, those are cable controlled, which means that you have an assembly where there is a cable running from one end, let's say upper extremities. This is amputated. There is a cable going from this prosthetic that I had to the other hand. When you move your hand, the cable will be, stretched, and that is going to cause the other prosthesis to make movement. Or something called externally powered prosthesis. This electrical powered prosthesis, you have batteries, and myoelectric prosthesis, this is controlled by the muscles. Switch control prosthesis, you can have a joystick, right, that can control that the arm, the thing that you do. Then we have hybrid, which is cable to elbow terminal device, but the battery power, a mix between the two of these thoughts. And those are example of the excursion to elbow, excursion to terminal device, and the powered elbow. It's just, I want to make sure that we know the terminology of the definition of those, and we would like to be focusing on electrical power prostheses. That's the main goal. Cosmetic prostheses, these are types of some prosthetics. Cosmetics is very important in patient life, especially for upper extremities, because they're visible. Lower extremities, they wear pants or they have these shoes, but the upper extremities are visible to the public, and therefore the appearance is important. Here we have something called matching skin tones and gloves that resemble human hands. As I said, it's expensive and hard to clean. And if the patient has one amputation limb, he or she might want prosthetic that is more cosmetically. Now, fingers, when these things are most commonly in industry because of industrial accidents, especially with machining. That's a big problem for us. Now, body part prostheses. So we'd like to talk about the parts of these prostheses. So this is similar to the picture that you've seen before. You will have something like this. Now, it's not cosmetically pleasing, but it's very functional. And you can control it easily with this wire. So you can, let's say, move the shoulder a little bit and that open or close. And what you want to do in designing these is to minimize the subject's movement and range, the space that they're moving. So you don't want to have someone in the street doing this in order to open and close the other. So we try to use the shoulder as much as possible. So the cables usually are moderate cost and weight, and they're functional, and they're durable. They have high sensory feedback. And what we mean by that is that you feel when you open and you close because you're moving your body parts. And we discovered that this sensory feedback is really very effective and useful for people. However, less cosmetically pleasing than the myoelectric control types, and is required more gross limb movement. So it needs to move your body a little bit more, in a wider space. We don't want to have something crazy, but you need to at least move that thing. And there's a lot of designs, actually. It's really an engineering problem, and creative solutions are available. And then we have externally powered prostheses. They're electrical motors, proximal function. They have more proximal function and a greater grip strength, and improved cosmetics. But the problem with those, they're heavy and expensive, and patient-controlled batteries. We need the battery, and that's also adding to the maintenance of it, that the subject need to take care of the battery itself. They have less sensory feedback. That's a disadvantage because it's controlled by them by machines and motors, and require more maintenance, and they require a control system. Now, this is something we like, and the control system is based on the Arduino, right? It's a microcontroller, and if we know how to work with the Arduino, you can do a lot of things for the prosthesis. Two types. We have something called Myoelectric and switch control. And you can see that this is your motors and the grip, but you can put a cover on it cosmetically, But there's a lot of moving parts, and that's a challenge. Now, mechanical engineering is studying moving parts, but since it interacts with a biological living system, we need to understand, the interaction with the body, and that's why it's a biomedical engineering challenge. Hybrid prostheses, they're mixed. So we can have myoelectric and body-powered prostheses combined together to enhance functionality. So you can have something like this with, sensors on the chest, contract the chest or, relax it. You can have a signal that can power the wire and open and close the wire. And we use it usually above the transhumeral level because you don't have much to work with, and you need muscle activity to be able to control it. Body prosthesis will control shoulder and elbow movement, and there are two joints now, and that's heavy. While the Myoelectric device will control the hand and the wrist function. So you can have something to attach to the body, but then you need to move the end effector. Typical components of upper extremity prosthesis. So if you have transradial, and that's the transient below the elbow, right? Include voluntary opening, split hook, that's the end effector to do things to open. Friction rest. Remember we talked about the friction with the feet, multi-axis and single axis, to make sure that it is not, loose. Then we have a double-walled plastic laminated socket, and the double-walled is because we would like to have the wire in it to control it. In lower extremities, we are not going to control that. You're not going to be moving your feet or the knee from another part of the body because that's very heavy for us. And then we have a flexible elbow hinge, and then we have a single control cable system or a triceps and then triceps cuff to hold it, right? And then we have a figure 8 harness, and there are different types of harnesses to stabilize that. Now this is transradial. Transhumeral, it's above the elbow, and they're similar but includes internal locking elbow because now it's becoming a heavy prosthetic, and we need to make sure that we have some locking mechanism so it does not fall. And we need to make sure to decide on using a material that is light. You need to have movement with the elbow. Use a dual control cable system instead of a single cable system because now you need to move two things. We have the wrist, whatever below the wrist, and then below the elbow. So you need to have two cables to control that. And then we need to teach the subject how to use it. It does not require a tricep cuff because we have the locking system. All conventional body-powered upper extremity have the following components. You have the socket, suspension system, and which is holding it, the harnesses. And then you have the control cable system, the terminal device, the end effector, and component for any interposing joint as needed according to the level of amputation. So you have a friction rest or or the elbow or the shoulder. So it's similar to what we had for the lower extremities. More information about the socket and what our people are using actually to include these. And then you have the suspension, and we have the suspension is in order to hold the prosthetic with the body. So harness-based system, self-suspension sockets, or suction sockets, similar to the lower extremity when we use negative pressures. That's what we do with that thing. Okay, harness-based system. You can go through this, but it's good information to learn about it, especially the Y strap and the different types of straps, and all of this is, if we would like to build something like that, this is important. But I would like to focus on the electrically powered prosthesis. That's what I want to be focusing on. And this is self-suspension, suspended sockets. And the suction systems, they have different ones. But the problem with suspension systems is the skin. You need to make sure that we don't have negative pressure that can result in ulcers for those. Now, control cable mechanisms. That's another thing that if you have a single or double, control cable systems, we're not going to be doing this or designing any of those. But it's good information for you to know about those things. Okay, now body movements that are captured for prosthetic controls, you can have something, and that's important from a clinical point of view. You need to make sure that we have something called glenohumeral forward flexion, biscapular abduction, which is chest expansion and relaxation, and we have the glenohumeral depression, elevation, extension, abduction. So there's all these movements. And if you remember from biomechanics, we did not talk much about the chest itself, but it's important now because of controlling the cable-powered, prosthesis. And we will have some pictures to look at those later on. Um, because when I move the chest, I'm going to be using the EMG signals to control the electrically powered prosthesis. Major function of the terminal device is the hand to replace gripping. That's the most important thing. And the gripping, they call it prehension. And the 5 different types of grips are follows. These are the types that we care about: precision grip, tripod grip, lateral grip, hook powered grip, and spherical grip. And each one of them, or each one of these grips actually is important to replicate using our end effector. So if you want to have really a functional, a very well designed end effector, you need to make sure that you have all of these capabilities for them. And each one of them has a different design and requirements to have. A hook grip is something just to hook on something and open, let's say, the door or closing the door. The tripod, you have 3 fingers and you open with those. Precision grip is that you want to precisely hold something, but you don't want to crush it. So you need to have some sensors with it. And this is something we can do actually. We can design something like that. And I have a couple of grips here, but they are only just the alligator grip, so it just closes on itself, two pieces. Spherical grip is that you would like to have something to hold spherical objects, because holding a ball is different from holding, let's say, a cup. And the hand is really, really a complex structure to allow us to do all these movements. You can select one of these, but it will be the best is to be able to design something that can do all of those for one subject. Okay, then we have, so I would like to go into the passive, and active terminal devices. Remember, passive is just cosmetic, and active is the thing that you will be able to do, functionality with it, and that's the main objective of the whole 2 categories. And then you will be having these examples. So this is just cosmetic. It has no functionality. This one it has the mechanical components in it that can move it, gripping. This is functional cable, activated terminal device, and that's myoelectric controlled. Also under functional prosthesis. We would like to design this. That's what actually we would like to spend time learning more about. This is really useful, but it's becoming, we have the technology, so why not use it and all that. Okay, so this is it for the upper extremity and the tissue integrity. We just want to make sure that we have at least an understanding of what is the tissue involved in amputations and different types of amputations and what are the parts of each of those.